Here is an example based on ideal transformer. Please pardon my writing. I'm going to read it. Consider a simple power system consisting of an ideal voltage source, ideal step-up transformer, transmission line, and ideal step-down transformer and a load. The voltage of the source is Vs equal to 480 volts. The impedance of the transmission line is 3 plus J4 ohms and load is 30 plus J40 ohms. If the transformers are not there, find the efficiency and voltage regulation. This symbol is called eta. Okay, we read it as efficiency. Okay, first let me go over first part. So here is a 480 volt source and the transmission line impedance and the load 30 plus J40 ohms. Voltage regulation is nothing but V no load minus V full load over V full load times 100. Voltage regulation tells us that how much voltage drop in the transmission line. So here is a transmission line. The transmission line has an impedance. So whatever the voltage we give, definitely there will be some voltage drop here. I mean, I can clearly see this is 10% of the load. So almost 10% of the voltage is going to drop there. Okay. Now 0% voltage regulation is excellent. Remember that. So lower voltage regulation, that means low voltage drop in the transmission line or low voltage losses. So whatever we are supplying, all the voltage we are getting at the output. That's an excellent voltage regulation. So our utility company is trying to get 0% voltage regulation. Now I'm going to find I total. I total is nothing but V over Z total. V is 480 at an angle of 0. Z total is these two impedances are in series. So 33 plus J44, which is 55 at an angle of 53.13. I total equal to 8.727 at an angle of minus 53.13. Now the load voltage is I total times Z load. So I multiplied those two. So 30 plus J40 converting into polar format, 50 at an angle of 53.13. I end up with 436.4 at an angle of 0. Most of the cases, this value is going to be 0 or close to 0. Okay, minus 2 degrees, plus 2 degrees, something like that. So we can ignore that angle. Now the voltage regulation is nothing but V no load minus V full load over V full load. So 480, that's the given value, V no load. That indicates that if nothing is connected here, then all the supply voltage will appear here, right? So that's what the V no load indicates. So 480 minus 436.4 over 436.4 times 100. Voltage regulation, we always say percentage, okay? So which is 9.99%. Efficiency eta is nothing but output power over input power times 100. Efficiency is always between power, not between the currents or between the voltages. It's always between the output power and input power. Efficiency is always either power or energy. Energy is nothing but power times time. So the time get cancelled out because the time frame is going to be the same. So efficiency is going to be always output power over input power times 100. This is also in percentage. So output power is nothing but power consumed in the load. So I already know the current here, which is 8.727 ampere. Okay, the power is always consumed in the resistor. Okay, the power, whenever I say power, I'm talking about active power. Okay, P. Okay, that power is always consumed in the resistor, which is I square times R load, 8.727 whole square times 30, 2285 watt. And P losses are IT square times R line, end up with 228.5. So efficiency is nothing but output power over input power times 100. So 2285 over 2285, which is output plus losses, times 100. It gives me efficiency is 90.91%. Now in part B, he's saying that now you have two transformers. One is ratio of 1:5 step-up transformer another one is ratio of 5:1 step down transformer. Now find the voltage regulation and efficiency. Now here is the circuit diagram look like. Okay, now we know that, so here I'm going to take this as N1 N2. Okay, whenever you see these two lines in between, that's an ideal transformer. So here these two transformers are ideal, so I can tell V2 equal to N2 over N1 times V1. N2 is 5, N1 is 1 times V1 is 480, so we'll end up with 5 times 480, 2400 volt. Now I'm going to take this voltage as E2. Okay, so if I apply KVL in loop 2, 3 plus J4 I2 plus E2 minus V2 equal to 0. So if I simplify, I2 equal to V2 minus E2 over 3 plus J4. Okay, now E3 over E2 equal to 1 over 5. E2 equal to 5 times E3. So after simplifying this, at the same time, according to transformer ratio, if I take this current as, I'm taking this current as I2, this current as I3, I3 over I2 equal to 5 by 1. So I3 equal to 5 I2. Based on this, I3 equal to E2 over Z load. And E2 equal to I3 times Z load. My apology, this must be E3. E3 times Z load. Okay. Now if you substitute all these equations, you end up with I2 equal to V2 minus 25 I2 times 30 plus J40 over 3 plus J4. That's very long process, right? So I will tell you a shortcut. Say for example, when it comes to the ideal transformer, I always tell you your P1 is same as P2, right? P1 equal to P2. So P1 I can write it as I1 square times whatever the resistance. Since this is an ideal transformer, there is no resistance here. Okay, I will say R equivalent, and P2 is nothing but I2 square R load resistance. Okay, so can I say R equivalent is nothing but I2 over I1 square times R load? So I2 over I1, can I say that value is 1 over N? Okay, we know that N2 over N1 equal to I1 over I2. I'm calling this as N, so since this is inverted, I2 over I1 must be 1 over N. So this R equivalent is nothing but R load over N square. N is nothing but turns ratio, sorry, not turns ratio, transformer ratio. N equal to N2 over N1. So by using this principle, what I can do, I can transfer this load impedance to the primary side. Okay, so when I transfer this to the primary side, my N here is 1 over 5. N square is nothing but 1 over 25. So this Z load is nothing but ZL over N square. So N square is nothing but 1 over 25. Multiply with 25, you will end up with 750 plus J 1000. Now this line impedance and load impedance, these two are in series. So basically what I did here in this diagram, I eliminated this transformer. Okay, eliminated this transformer. Now I connected the load right here. Okay, I'm calling this as ZL prime. Whenever you transfer impedance from one branch to the another branch, you indicate with the prime. Okay, ZL prime. So this ZL prime is, I have that value as 750 plus J 1000. Okay, so ZL over N square, 750 plus J 1000. Now I found I2. I have this 2400 based on the first transformer transformer ratio. Okay, so here you have 480 volts. So based on this, I end up with having 480 or 2400 volts. So I found the current I2. So based on I2, now I can use the same values, don't need to transfer again, okay, to find out the efficiency as well as the voltage regulation. So I found the voltage drop across the load is 2387.5, okay, and the power consumed in the load I2 square times RL, and then power losses are I2 square times R line. So this is load and line, don't confuse with RL. So percentage of voltage regulation, I'm giving 2400 at no load. Full load, it is 2387.5. Okay, as I mentioned, don't worry about this angle. Most of the cases, this angle might be like 1 degree, 2 degree. Okay, so we can ignore that angle. So percentage of voltage regulation is very little, like 0.5%. So previous case, without transformer, we lost close to 10%. Now it is only 0.5%. That is the advantage of the transformers. Another one, efficiency. Efficiency is output over input. So whatever the load is consuming divided by P load plus P losses. Load is consuming this much, losses are only 10 watts. So now I have 99.6%. So previous case, I think I have close to 9.9%. Now I have only 0.4%. So lots of power saving. That is the main advantage of transformers. The last part he is asking about, to have 1% of losses, what will be the ratio of transformer? This is transformer, simply XMER. Okay, transformer. So what I'm going to do here, I'm going to transfer this load into the primary side of the second transformer and everything into the primary side of first transformer. So when I transfer this, Z load is nothing but Z load over N2 over N1 square, so we'll end up with N square. So that I'm going to indicating that as Z prime load. Now again, I'm transferring this to the primary side. So when I do it, Z double prime load, the N value is same in both, but here this is 1 over N, this is N. So 1 over N, again, you're going to have Z load N square over N square. So this N square get cancelled out. So Z double prime load is nothing but you will end up with the Z load. And the line is Z line over N square. The N is right there. Okay. Now efficiency is nothing but output over input times 100. So what is he saying? He want to have only 1% of the losses. So efficiency is 99%. So 99% equal to P output over P output plus P losses times 100. Okay, 99% is nothing but 0.99. 0.99 times output power is nothing but I square times R load over I square times R load plus I square times R line over N square. Okay, so Z prime line is nothing but Z line over N square. Okay, now I square is common, I can eliminate that, and the load resistance is 30, line resistance is 3. So I substitute those numbers. Okay, end up with 1 over N square equal to 0.101, 1 over N equal to 0.317. That is N1 over N2, because N is nothing but N2 over N1. So since this is 1 over N, you will end up with N over N2. So N1 is to N2 is nothing but 1 is to 3.146. Okay, that's a long video, but you may need to go through it a couple of times to understand it better. Please let me know if you have any questions. Thank you.